Consider the Earth and a rocket ship which are bound together by gravity. If it takes work or energy to pull them apart, then the binding energy is the amount of energy it takes to completely separate them. Similarly, the binding energy in a nucleus is the amount of energy it takes to completely separate the protons and neutrons, collectively called nucleons. There are two forces acting inside the nucleus of atoms. The nuclear force, a residuum of the strong force that holds quarks together, is pulling the neutrons and the protons together, and the electric charge on the protons is pushing them apart. The strong force is a lot stronger than the electric force at short ranges up to 2.5 times the proton diameter. But at larger distances, the electric force dominates. So as we add nucleons and work our way up the chart of the periodic table, initially each nucleus is generally a little more tightly bound than the one before. This chart gives the actual numbers. This increase in binding energy continues until we get to iron and nickel, where the nucleus has about 60 nucleons in it. At this point, the nucleus has a radius more than 2.5 nucleons wide, which you remember is the range at which the repulsive electromagnetic force begins to dominate. So as we add nucleons past this point, the electric force trying to tear the nucleus apart starts winning, and each added nucleon is a little less tightly bound. When we get to lead and bismuth, and the nucleus contains 207 nucleons, the electric force wins, and the atomic nuclei larger than this are unstable and come apart by themselves, although it may take a while. These larger nuclei can return to more stable arrangements in several ways. They can convert neutrons into protons and give off beta radiation, or kick out whole groups of nucleons, 4 at a time, in alpha radiation. Or they can simply split into other smaller, more stable nuclei. When this happens, we call it fission. Fission is different from the other forms of decay because it can be harnessed and controlled via chain reaction. Now let's consider what this means from an energy perspective. According to the binding energy chart, uranium has 7.6 MeV of binding energy for each nucleon, for a total of 1,786 MeV, while barium-144 has 8.3, and krypton-89 has 8.8, and the extra neutrons have no binding energy. So every time a nucleus of uranium fissions, we get about 192 MeV of energy. But U-235, left to its own devices, might take billions of years to decay, so we will want to help it along. We do this by shooting a slow neutron into it. It absorbs the neutron and briefly becomes U-236. Then it splits into krypton-92 and barium-141 and three neutrons. Those 3 neutrons go to split other U-235 atoms into other daughters of more neutrons, and the process grows and repeats again. We can put the whole thing in water, and the daughter fragments and neutrons will be slowed by the water and cause it to heat up. Finally, we can use the steam to make electricity. This is how a nuclear power plant works. Ever since Einstein demonstrated the equivalence of mass and energy, physicists often give the rest mass of tiny particles like protons, neutrons, and electrons in units of energy. 2 convenient energy units are the electron volt, or eV, and its cousin, million electron volts, or MeV. Using these units, here are some facts that will come in handy. The rest mass of the proton is 938.272 MeV. The rest mass of the neutron is 939.566 MeV. Let's take another look at the chart of binding energy of atomic nuclei. And now let's talk about fusion. If we can take a nuclei of deuterium, which has one proton and one neutron in its nucleus, and get it to fuse with a tritium nucleus, which has one proton and two neutrons, we would end up with helium, one extra neutron, and some energy, and we would have the basis for an energy-making machine. Let's run the numbers and see how it works. The binding energy for deuterium is about 2 MeV, and the binding energy for tritium is about 8 MeV. So the total for the input items is 10 MeV. The binding energy for helium is 28 MeV, and the free neutron has 0 binding energy. Subtracting the 10 MeV from the 28 MeV reveals that every time this fusion happens, we liberate 18 MeV of energy. And that's pretty good. But there's a problem. Getting the protons in the deuterium and the tritium close enough together so the nuclear force fuses them together is hard to do on Earth. This is the energy that powers the sun and the stars. But the sun's gravity holds the fuel in place, while the high temperature gives the nuclei enough speed to overcome the electric repulsion. If we could make a miniature star in the lab, a microsun, then we would be well on our way to having a great solution to our energy problems. And although this has proven difficult, significant progress continues to be made. Similar to tritium is an isotope of helium called helium-3. It could be substituted in the above reaction and would produce a similar amount of energy. What's the difference? Well, there's an estimated 1 million tons of easily mined helium-3 on the moon's surface. It would only take 25 tons to satisfy all the energy needs of the United States for an entire year. And 25 tons also happens to be the maximum payload of the space shuttle. And now you know why we're going back to the moon. Why is gravity so weak? Why can a small magnet pull or push something away from the entire Earth? There is an idea that may explain it. But before we go there, let's explore more preliminary ideas first. The most popular quantum gravity theory of today describes all fundamental particles as vibrating strings of energy. And the theory is constructed in a whopping 9 or 10 spatial dimensions instead of the 3 that we experience in our everyday lives. But what is a dimension? A line is a familiar geometric figure and can be completely described by giving its length. It is a one-dimensional object. It can be imagined that the dimensionality of an object can be created by taking an object of one less dimensions and moving it at a right angle to that dimension. You can create a line in your imagination by thinking of taking a point and moving it. Next, consider a surface. A surface is also quite familiar. A surface has both length and width and requires 2 measurements to define it. and therefore is a two-dimensional object. Similar to a generation of a line from a point, we can generate a two-dimensional surface by taking a line and moving it in a direction other than the direction of the length. And a solid figure is the stuff of everyday life. It has length and width and depth, and requires 3 measurements to describe it, and is a three-dimensional object. And like the generation of a surface from a line, we can generate a three-dimensional object like a cube by taking a square and moving it in a direction other than the direction of the length and the width. Cylinders, cubes, and spheres are three-dimensional objects. And now the hard part. The higher dimensions are created by moving a three-dimensional solid in a direction other than the length, width, or height. And while that is easy to do mathematically, it is impossible for us to picture it. So let's examine how we might detect these other dimensions. We begin with bright light spreading out in a spherical shell. The intensity of the light at any one point will fall off the square of the distance from the source, because the surface that the light covers grows as the square of the distance from the source. But that is only true in three-dimensional space. In four-dimensional space, the light will grow dimmer as the cube of the distance. And in 5 dimensions, it will grow dimmer as the fourth power of the distance. And in 10 dimensions, it will grow dimmer as the 9th power of the distance. Now back to strings. If this membrane represents the 3 dimensions that we live in, then particles like quarks and electrons are the strings that have the endpoints forever attached to those 3 dimensions. They might look like this. But the particle that is the force carrier for gravity, the graviton, is a closed loop. It has no ends that are constrained to our 3 dimensions. So if there are other dimensions, gravity will propagate freely there as well as in our familiar 3. And that might explain why gravity seems so weak to us. We experience only a tiny fraction of gravity's true strength because so much of it is leaking out into other dimensions. But where are these dimensions hiding? One possibility, but not the only one, is that they're all around us, but incredibly tiny. If you look at a wire or a string from far enough away, it looks like a line, a one-dimensional figure. But if you get closer, or if you were a lot smaller than the thickness of the wire, then you would easily see that it has other dimensions. On the tiniest of scales, space has extra dimensions at every point. It might look something like this if we were small enough to see it. Accelerators like the LHC at CERN smash protons against antiprotons at enormous energies, perhaps enormous enough to produce gravitons. And if they do, then perhaps we might just be able to see them form in our limited 3-dimensional world and slip quickly and quietly away into those hidden dimensions.
We now examine a phenomenon which is absolutely impossible to explain in any classical way, and which is at the very heart of quantum mechanics: the famous double-slit experiment. To understand this experiment, we first need to see how ordinary particles, or little balls of matter, act. If we shoot small objects, such as marbles, at a screen containing a single slit, we see a pattern form where they went through the slit and hit on the back wall. Now, if we add a second slit, we would expect to see 2 bands directly behind the slits. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we shoot particles such as matter through two slits, we get this: two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marbles, a single band. So, if we shoot these tiny particles through two slits, we should get, like the marbles, two bands. What? An interference pattern? We fired electrons, tiny bits of matter through, but we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off of each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither, and it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So, they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. This led to many questions. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? It was as if the electron decided to act differently, as though it was aware it was being watched. It seemed as if the observer somehow collapsed the wave function simply by observing. However, physicists eventually realized that any type of measuring device, no matter how small, always interacted with the electron, subsequently destroying the interference pattern. Werner Heisenberg proposed a new uncertainty principle describing this. The uncertainty principle can be stated in terms of our experiment as follows. It is impossible to design an apparatus to determine which slit the electron passes through that will not at the same time disturb the electron enough to collapse its wave function, destroying the interference pattern. And it was here that physicists stepped forever into the strange never-world of quantum uncertainty.
What is the temperature of outer space? Way out there, between galaxies, where there is only one hydrogen atom per cubic meter. Can an individual atom be hot or cold? Can it even have a temperature? It sounds a little silly to say an atom is 27 degrees Fahrenheit or something. But temperature really is a measure of the motion energy of an atom. If an atom is motionless, then it is at 0 Kelvin. We don't say degrees Kelvin anymore. Now, it can never be really motionless, so it can never be at exactly 0 Kelvin. And it moves pretty fast as temperatures rise. At a tiny fraction of a degree above absolute zero, the atom is already moving at about 1 centimeter per second. For subatomic particles, the energy is often measured in MeV or GeV. An electron with 1 GeV of energy is moving close to the speed of light, and that corresponds to a temperature of 11,000 billion Kelvin. For a collection of atoms or molecules like a gas or a crystal lattice, the temperature of the collection is just an average temperature of the group. But of course, because of collisions and interactions at the molecular level, a group of atoms or molecules will distribute the total motion energy pretty evenly among the individuals in the collection. And if two or more systems are brought together, some motion energies from the hotter system will flow to the colder system until they are both at the same temperature. When you measure your body temperature using a thermometer, your body cools down a tiny bit, and the thermometer heats up until the two are at the same temperature. Then reading the thermometer's temperature also reveals your body temperature since the two are the same. If we take a quantity of gas and enclose it in a container, the individual molecules in the gas consistently bang into the walls of the container, creating a pressure on the walls. We can do 3 different things to increase the number of wall collisions. Increase the number of atoms in the container by adding more gas. Or increase the motion energy of the atoms already in the container by heating the gas. This makes them go faster and increases the number of times that each atom hits the wall. Or we can make the container smaller, decrease the volume, so that the individual atoms have shorter distances to go to collide with the wall. This leads directly to the ideal gas law, relating temperature, volume, pressure, and quantity of gas. Snuck that one in on you, didn't we? It all started with light, smart light. Then it quickly spread to rocks and other projectiles. Now it's seemingly everywhere. But before I tell you about that, consider how smart people react to certain situations. If I have a trial where you have to start at point A and run and touch any point on the wall, and then run to point B, how do you decide what is the quickest path to take? And how do you decide where to touch the wall? You could run to here, or here, or here. But after a moment, you pick this point because you think it's the shortest path and results in the quickest journey. In a second trial, you are a lifeguard and you spot a swimmer in trouble out in the water. How do you decide the quickest path to the swimmer? You run faster than you can swim. So do you run to this point and swim from there? Or maybe this point? If you choose correctly, your path will be the path of minimum time, and you will have joined the ranks with Fermat, Maupertuis, Euler, and Lagrange in furthering one of the most universal principles of nature. Living in the first half of the 17th century, Pierre Fermat developed the concept that light travels at different speeds in different media, and maintained that the path the light takes is always the one that takes the least time. His detractors at the time gleefully pointed out the obvious objection. How does the light know which path will be the quickest? Smart light? Pierre-Louis de Maupertuis, the son of a wealthy pirate, expanded Fermat's least time idea. He wrote that in all events in nature, there is a certain quantity called action, which is always a minimum. His good friend and mathematician, Leonhard Euler, added the idea of conservation of energy and made least action an exact dynamical theorem with this mathematical form. Euler also developed an ingenious graphical method to find the path of minimum action for a system. Another young scientist of the time, Joseph Louis Lagrange, eagerly applied these ideas to the Tantachrone problem. This is the problem of finding a curved shape on which a weight started at any point on the curve will slide to the bottom in the same amount of time, regardless of its starting point on the curve. He expanded the idea of action to be the function of kinetic energy minus the potential energy. This is proven to be a much more universal formulation. Now that we know all of this, let's throw a smart baseball straight up with enough force that it returns to our outstretched hand 3 seconds later. And let's see if we can discover its motion using the principle of least action. When we first throw it, it has a lot of kinetic energy, and its speed is at a maximum. But gravity slows it down as it rises. At its peak, its speed is 0, and all of its energy has been transformed to potential energy. On the downward trip, all the potential energy gets reconverted into kinetic energy. Its kinetic energy is related to its speed, and its potential energy is related to its height. Now on this graph, we have the baseball's height on the y-axis and the time on the horizontal axis. To begin, we have divided the 3 seconds of flight time into a few time intervals. As we adjust the height of each point, the computer will calculate the total actions for us. Remember, we're looking at the minimum actions possible while keeping the ball in the air for 3 seconds. The height of the dot is directly related to the potential energy, and the slope of the line gives the speed, which is related to the kinetic energy. The steeper the slope, the faster the baseball is moving. As you can see, it is an iterative process. It will take several cycles before we can no longer make the total actions any lower. That is, less negative. Here's the same problem with more sections in the graph. To do this perfectly, the number of sections must go toward infinity, and the width of each section must go towards 0. But this approximation with 40 sections is good enough to show all the features. Now that we have the motion, let's examine the path, or world line, and see what we can see about how smart that baseball really is. The numbers to the right list the change in velocity for each segment, as well as the acceleration for each segment. You can see that the change in velocity is constant from section to section, and the acceleration is equal to the standard value for the acceleration of gravity, 9.8 meters per second squared. Since we are on a roll, let's do it one more time, showing for each section the kinetic energy, the potential energy, the difference between the two, as well as the total energy. Adding the t minus v column gives the total action, which is smaller on the path than any other possible path. You can also see that the total energy is constant, as it must be if energy is conserved. And to demonstrate how versatile this baseball is, let's throw it onto the roof of a house, so the endpoint is 4 meters higher than the initial point. Method still works pretty well. Smart baseball. While everyone has heard of Isaac Newton and force equals mass times acceleration, it is this other equivalent formulation of kinematics that is more versatile and has direct extensions into relativity and quantum mechanics. So, how does the light know which path to take to satisfy the principle of least action? Richard Feynman gave us the answer, and we will explore that answer in another video on QED. This is a photomultiplier. It counts individual photons. This is one easy way that we know photons are particles. If light wasn't made up of particles, we couldn't count them. Every instrument that has ever been designed to detect weak light has shown the same thing. Light is made up of particles. Today we are going to examine how light interacts with matter. And all you need to know about light to follow along are the familiar everyday properties of light. Like light goes in a straight line. It bends when it goes into water. When it reflects off a mirror, the angle at which it hits the mirror is equal to the angle at which it leaves the mirror. Light can be separated into colors. You can see beautiful colors on a puddle if there's a little bit of oil on it. A lens focuses light, and so on. Almost everyone has experienced looking out a window and seeing themselves partly reflected in the glass. Let me tell you about an experiment in which photons of just one color, say red, are emitted from a light source down towards a block of glass. A photomultiplier is placed at point A above the glass to catch any photons that are reflected from the front surface. And another photomultiplier is placed at point B inside the glass. And we find that on average, every 100 photons that we shine straight down on the glass, only 4 arrive back at A, while 96 arrive at B. But now we have a real problem. If we think about each photon encountering the glass, we might wonder, how does a photon decide whether to go through the glass or reflect back into the room? Okay, let's do it again. Only this time, we replace the block of glass with a thin sheet of glass, and we move photomultiplier B to the other side. Now the photons can reflect off either the front or the back surface of the glass in order to show up at A. We might expect that 4% would reflect off the front surface and 4% of the remaining photons to reflect off the back, making a total of about 8%. But what we find is that with some sheets of glass, 15 or 16 photons find their way back to A, and with other sheets of glass, we get only 1 or 2. Some sheets of glass reflect 10%, and others eliminate particle reflections altogether. After checking the glass sheets very carefully, we find they differ in only one respect. They vary ever so slightly in thickness. With this as a clue, we redo the experiment with progressively thicker and thicker glass. And sure enough, we see the particle reflection vary from 0 to 16%, and back to 0, and back to 16%, and back to 0 in a continuous cycle. Wow, how can that happen? How can adding a second surface somehow turn off the reflection from the front surface? How does the photon know how many surfaces it will encounter before it gets to them? The answer is that each photon travels every possible path simultaneously. There's no decision making at all. And the probability of each final outcome is determined by adding the probability from each possible path. And each individual path probability can be represented by a little arrow, such that the actual probability is the square of the length of the arrow. For example, in the first experiment, we found that the probability that the photon would arrive at photomultiplier A was 4%. That corresponds to an arrow whose length is 0.2, because 0.2 squared is 0.04. In the second experiment, there are 2 paths for the photon to get to A. So there must be 2 arrows, and we must add them. But how do we add arrows? We simply put the tail of the second arrow at the head of the first and draw a new arrow from the tail of the first to the head of the second. Now, to determine the direction that each arrow points, imagine that there is a stopwatch that times the movement of the photons along a path. When the photon leaves the source, we can start the stopwatch. And when the photon triggers the photomultiplier, we can stop the stopwatch. And whatever direction the hand points is the direction of the arrow for that path. Except we need one more rule. When the path includes reflection off the front surface of the glass, we reverse the direction of the arrow. Let's draw the arrows from the case of light reflecting from a very thin plate of glass. For the front reflection arrow, we start the stopwatch when the photon leaves the emitter. It bounces off the front surface and enters the photomultiplier, and we stop the stopwatch. Then we draw a little arrow of length 0.2 in the direction opposite that of the stopwatch hand. For the back surface reflection arrow, we repeat the procedure. And when the photon arrives at the photomultiplier, we see that the stopwatch hand is pointing in almost the same direction as for the other path. Because the glass is so thin, the back reflection path is about the same length as the first, and the stopwatch hand has turned only a tiny bit more. So we draw a little arrow of length 0.2 in the same direction that the stopwatch is pointing. Now let's combine the arrows. Since they are nearly the same length but point in the opposite directions, the final arrow has a length of nearly 0, and its square is even closer to 0. So the probability of light being reflected from a really thin layer of glass is essentially 0. As we replace the glass with increasingly thicker pieces, we can see that the stopwatch for the second path would turn more and more as the path gets longer. So the resultant arrow gets longer and longer as well. And the probability of reflection grows. When the glass is just thick enough for the stopwatch to make a half turn, the length of the two arrows add to give us 0.4. And the probability of reflection is the square of this, or 16%. As the glass keeps getting thicker until the stopwatch has made a complete extra turn, the resultant arrow is back to 0, and the probability of reflection is back to 0, and the cycle starts again. If we repeat this experiment with other colors of light, we would get similar results. Depending on the thickness of the layer of glass, we would get repeating cycles of reflection probabilities ranging from 0% to 16% and back to 0. But with one difference. The stopwatch hand turns at different speeds for each different color of light. So the thickness of the glass that results in 0% or 16% reflection is different for each color. And that explains the colors we see when the light is reflected from a thin film of oil on a mud puddle. The oil film is never exactly uniform in thickness, so different sections of the film are just the right thickness for reflecting red light, or blue or green light. So we see the entire rainbow of colors reflected from different areas of the film. Now let's replace the glass with a mirror. We move the light source off to one side and move the photomultiplier off to the other side. And let's add a screen in the middle so the photons can't go straight from the source to the photomultiplier, but we have to reflect off the mirror. Now our experience suggests to us that the photons will bounce off the center of the mirror because that's where the angle of incidence is equal to the angle of reflection. And our intuition makes it seem obvious that the parts of the mirror out to the ends don't have much to do with it. But that would take us back to the concept of smart light. How does the light know that it's supposed to travel in a single path? So let's examine how our idea that light travels every path can give us the right answer. Start with the fact that light has equal probability of reflecting off the mirror at every point. So when we draw our arrows, they will all have the same length. And let's simplify the situation by first looking at the 15 representative paths. These paths. Now, as we said before, the length of the arrow for every path is the same length, but we still need to calculate the direction for each arrow. And remember that the direction is determined by how much the stopwatch has turned during the photon's trip. The paths out near the ends of the mirror are the longest. Not only that, the change in length from path to path is greatest out near the ends as well. So the adjacent arrows will turn a lot from path to path. The first four will look something like this. As we get closer to the middle, the paths get shorter, and the difference in path length from path to path is much smaller. So the arrow turns a lot less for adjacent paths. The next 7 arrows look something like this. And the arrows for the paths at the right end are just like the arrows for the similar paths at the left end. Now let's join the arrows head to tail and draw the final arrow. And what do we see? First, the ends of the mirror are not important because the times are different from path to path. The arrows from the first part just go in a spiral. If we chopped off the ends of the mirror, it wouldn't change the end result very much. And the paths near the center contribute most to the final arrow. This is where the time of travel is the least. This is where the angle of incident equals the angle of reflection. And that is why you can get away with saying that light only reflects off the single point in the middle, even though that it's wrong. Let's test the idea that reflection is really happening all over the mirror. Let's remove the parts of the mirror in the middle and on the right, leaving only this portion on the left. And now let's force the arrows on the left to point in pretty much the same direction instead of pointing all over the place. We do this by noting how fast the stopwatch is turning, and by scraping away all the portions of the mirror that would give arrows that point to the left. Now when we add our arrows, we get a final arrow of substantial length. So we should get a strong reflection from our off to the side scraped up mirror. Does this really happen? Yes, it does. This type of mirror is called a diffraction grating, and it works like a charm. And since the stopwatch spins at different rates for different colors, the spacing in diffraction grating changes from different colors of light. But instead of actually changing the spacing, we can just move the photomultiplier up and down a bit. Changing the angle achieves the same end as changing the spacing. This is why a series of grooves, like on a music CD, reflect different colors of light at different angles. So a grating shows that light really reflects from all parts of the mirror, and light isn't so smart after all. We could continue describing interference and other phenomenon with our every path method and spinning arrows, but suffice to say, the method works. Always works. Exactly works. So let's turn our attention to the interaction of light and electrons. We can apply the every path method here as well. We start by drawing diagrams of every possible path for an interaction to occur. And surprisingly, we can reduce the task of making these diagrams to just 3 fundamental actions that we need consider. Every possible interaction diagram can be reduced to combinations of these 3. 1. A photon goes from place to place. 2. An electron goes from place to place. 3. An electron emits or absorbs a photon. Each of these basic actions has an amplitude, an arrow, that can be calculated according to certain rules. Let's draw a diagram of one action. A photon goes from place to place. We put time on the vertical axis and space on the horizontal axis, and we will represent the photon by a wiggly line. So basic action 1 looks like this. There is a certain probability amplitude for the photon to go from A to B. Let's call it P, A to B. And there is a formula for the size of the corresponding arrow. In the second basic action, an electron goes from point A to point B. Let's call the amplitude for this action E, A to B. Notice electrons are represented as straight lines. The formula for the amplitude of this action includes a very special number called n. And it's interesting to note that the formula for P, A to B, a photon going from point A to point B, is the same as E, A to B, an electron going from point A to point B, if n is set to 0. The third basic action is an electron emits or absorbs a photon. This action is called a coupling. Every coupling is a junction between 2 straight lines and a wavy line. There's no complicated formula for the amplitude of coupling. It is just a number, and we call it J. Its value is about negative 0.1. Now let's calculate the probability that two electrons at 2 points, 1 and 2, end up at points 3 and 4. This event could happen in two ways. The electron at point 1 could go to 3, given an amplitude of e 1 to 3, and the electron at 2 goes to 4, giving e 2 to 4. So the overall amplitude for this path is e 1 to 3 times e 2 to 4. Another way would have electron 1 go to 4 and electron 2 go to 3. This would have an amplitude of e 1 to 4 times e 2 to 3. And of course, the final step is to add these two arrows to get the total amplitude. This would be a good first approximation, but we should also consider other ways this event could happen. For each of the ways we just described, one electron could emit a photon on the way, and the other electron could absorb a photon along the way. Calculating this complicated amplitude involves the number j we mentioned earlier. It is shown here. And there are more possibilities. This looks hopeless, but the number j will come to our rescue. The first ways this event could happen have no j's in the calculation. The next way had j times j. And the last would have j times j times j times j. And since j times j is less than 0.01, the arrow from this possibility is only 1% as long as the arrow for the first way. And the j times j times j times j path is less than 1/10,000th as long as the no j method. So you only have to go to the more complicated possibilities if you need increased accuracy. When an electron is placed in an external magnetic field, it exhibits a response called its magnetic moment. The diagram for the first approximation of the magnetic moment of an electron is very simple. An electron goes from place to place and couples with a photon from a magnet. This gives a value of 1 for the magnetic moment. After some years, it was discovered that the value was not exactly 1, but something like 1.00116. In 1948, the first second-order corrections were made. They involved j times j terms from diagrams like this. To calculate the contributions from this class of diagrams, we had to make an arrow for every place in space-time that the photon could be emitted and every place that it could be absorbed. And since then, experiments have measured the magnetic moment to even greater accuracy. So now we needed to consider all the ways the electron can go from place to place with 4 extra couplings. It took 2 groups of physicists 2 years to calculate these terms. The term with 6 extra j's involves even more possible ways the event could happen. It took 20 more years to get this extra accuracy figured into the theoretical value of the magnetic moment. With better computers, more and more j's have been added. And theory and experiment now agree in more than 16 decimal places. If this accuracy was matched in measuring the distance from the Earth to the Moon, we would know the lunar distance to an accuracy smaller than the thickness of a single human hair. Quantum electrodynamics is perhaps the single most successful physical theory ever devised. It forms the bedrock foundations for all of today's unification theories, like the Standard Model. QED, Quod Erat Demonstrandum,